I didn't deserve it, but. All right, so let's get into some practice of Ohm's law. A lot of these are going to be, like I said, the heart and soul of electronics. You're going to be using these all the time. Everything we go through to solve, it just depends simply on what's being asked. All right, so first thing we're going to do is we're going to look at our basic circuit. We're going to have our DC supply, which could be the supply, a battery, whatever it may be. So we'll just say 3 volts. We have a polarity on these guys, of positive to negative. We've got R1, and we're going to label this as 1 kilo ohm. So one of the ways that we designate things in electronics is we use a subscript notation. So we indicate what we're talking about. So in this case, a resistor, which we designate as R because it's the thing. The voltage supply, we're going to designate with a V. And then the subscript notation is where we put it in small letters underneath of it to designate what is what. So we have a voltage source, and we have resistor 1. This is going to come important because as we start going through these, we're going to start building into circuits that have more and more components. Getting to the point where we have 7, 8, 9, 10 components in one circuit. And we have to be able to go through and designate which values are for which components. And that's where this designation comes in from. It honestly does not matter what you use, as long as you are consistent in what you use. Everything that we do for this resistor needs to be designated as R1. I could go through here and I could call this R-Tom if I really wanted to. It doesn't matter. It's just a label. A lot of times I will put descriptors and stuff on here depending on what they're going to be used for, just to kind of help me remember what am I supposed to be doing. But most of the time they're going to just be labeled simply as R1, R2, R3, capacitor 1, 2, 3, so on and so forth. We'll talk about more about the subscripts later when we get measuring through these. So the first thing we need to look at is, based on this circuit, we need to understand how is the electrons going to flow in this circuit. There's 2 ways to go about this. We have electron current flow and we have conventional current flow. So electron current flow basically states we're going to follow the path of current based on how the electrons are moving. Okay? So the electrons are negatively charged. They're going to be trying to get to the positive poles. So they're going to travel in this direction. That's electron current flow. We go from the negative pole to the positive pole. That's basically saying we're just following the path the electrons are going to take. Now, the converse to this is conventional current flow. Basically what this is saying is we're going to be following the change of charge going through this. So in this sense, we're going to go from the positive to the negative. And that's just because some people find it easier to be going from a positive, from a high point, to a low point. We kind of will bounce back and forth between the 2 of them. It honestly does not matter which direction we're using as long as you understand what are you chasing after. Are you chasing after the electrons? Are you chasing after the charge? Okay. Most of the time I use electron current flow because that's the way I was taught. But either way, we're going to bounce back and forth between them depending on the situation. Both of them are correct. You just have to make sure you label and understand what is your current doing. So with it, yes?
So is that because some, when you're testing the voltage, in some it'll be negative or something?
Yes. That's more of about where is your ground. That where's your reference point. So right now, generally when we're talking about these guys, we're going to assume our reference point, if we have one, is off the negative terminal of our supply. So if I don't put it up there, that's what we can kind of safely assume that that's where our reference point is going to be. This can move depending on how we want the circuit to work. So we can move our reference point wherever we want. We just have to indicate where it is. But if we don't, we just need to make the assumption that it's off the negative of our supply. That makes sense for now? Like I said, when we get into more complicated circuits, this is going to move and you'll see why that's important. So going through this either direction, we have to look at, okay, where is everything connected to? What are my values going to be? What's going on in the circuit? One of the things we have to be aware of is we can kind of look at these and we can start to get an idea, what is the polarity of these voltages going to be? How are we going to measure these? Okay. One thing we're going to look at is we're going to see what side of the component is connected to what side of the power supplies. So when we look at this, our resistor is going to have a charge of positive to negative in that order, because this side of the resistor is connected to the more positive side of the battery. This side of the resistor is connected to the negative side of the battery. So we're going to have a potential difference in there. When we measure voltage, this is what we're going to get. This right here is a series circuit. It has one path for current to flow through. We start at one terminal, we go around through the components, back into the battery. One path, series circuit. Okay, this is the very basics of how we can get there. We will get to the point where we'll start adding in more resistors as we go. So right now we're going to look. One of the things we have to know too is that we have to have all the voltage in our circuit that our supply is dropping has to be dropped everywhere in this circuit. We can't lose power, we can't create power, we can't lose energy, we can't create energy. It's the law of conservation of energy. We have to maintain those balances. We're not just going to randomly dissipate 4 volts and be okay with it. It went somewhere. So in this case, we want to know what is the current total for the circuit. How much total current do we have flowing through here? How much current do we have flowing through R1? So here is our designation, current total, current through the component R1. We want to know what our power total is. We want to know the power through R1. Because if we're going to build this thing and measure it, we have to know what size of resistor do I have to put in here to keep it from burning up. And so it'll just work like it's supposed to. So a lot of times in the examples, what we're going to be doing is I'm going to give you this format, or I'm going to give you some formula or a circuit, and then I'm going to have a list of stuff that we're going to find. So I'm going to be giving you the circuit. This is what we want to find. Show me the work of how to get there. Okay? So the first thing we want to look at is we want to look at total current. Total current, what is the formula for solving for current? I'll keep those up on the board. So what do we say current was? Voltage over resistance. So in this case, we have to look at how much total voltage do we have in this the circuit? How many sources do we have? One source, and it is 3 volts. We look at this circuit. How many resistors do we have? 1 resistor. So what's the resistance total? 1K. So, or 1,000. One thing that also helps is make sure you include your units when you are doing your calculations. They will save you more times than not, because you'll be looking at something and you're like, wait a minute, I'm taking a number that's volts divided by volts. That's not going to get me anything. That's going to leave me unitless. Okay, there's going to be nothing that converts to. I did this on a test in high school. I divided volts by volts to get me ohms. And you know what my teacher did? Made fun of me profusely for it in front of the class. Her name was Mrs. Watts. It was actually kind of funny. She was our electronics teacher. A lot of respect for that lady. She's the one who gave me my desire and my passion for this. But it was funny. I never did that again. So make sure you maintain the units that you're working in and make sure that they're going to come out to be the right. So we have volts divided by ohms, which is going to give us what? Current, which is measured in amps. So volts divided by ohms is amps. Any questions about that? Okay. So now that we have our formula, what is the current total for this problem? 3 milliamps. So it's 0.3. So 0.3 amps. We can also convert that into milliamps. So if we want to convert this to 3, so remember this is 0.3 times 0.003. Come on. Okay? Both those are correct, right? The other way we can look at this is we can shift this down. For me, that's kind of a lot of things to write. To shorten it down, let's convert it into milli. What is milli? What power is milli? -3. So if we want to convert this guy to 10 to the -3rd, what do we have to do? To the right. How many spaces? 3. So we do that. This becomes 3 times 10 to the 3rd, or 3 milliamps. Both those answers are correct, but again, we want to look to see what does the test or question want the answer to be in. Okay? And there will be sometimes that you'll see it either wants it in amps or it wants it in milliamps. Make sense? So we have 3 milliamps running through this circuit for our total current. Okay? So let's go ahead and let's look at R1. So how many components are in the circuit ignoring the source? One component. So what did I say about the voltage? Has to be the same as what's supplied as what's being used, what's being dropped. So where's that 3 volts going to go in the circuit? R1. So the voltage across R1 is equal to 3 volts. Because there's only one component there, has to drop all the voltage in there that we're supplying into the circuit. It can't just magically disappear. So then we look at this. So we have this one is equal to 3 milliamps. We want to find the current for R1. So again, what's our formula for current? V over R, voltage over resistance. And in this case, we're looking specifically at R1. So the voltage drop across R1 versus the value of R1. So what's our voltage drop across R1? 3 volts. And why? It's the only thing in the circuit. Like I said, these ones are going to be very easy and very basic. How much resistance do we have? 1 kilo ohm. So that gives us how much current? 3 milliamps. One of the things too you want to do is make sure you box your answers. That way, just kind of get into that habit. That way you can quickly find what you're looking for. That way you can know, okay, because we're going to be doing some work here in the end of, middle of next semester, where it's going to take up most of a page to do one problem. There's a lot of conversions that we have to go on. You're going to be doing a lot of information. This helps you quickly identify where your answer is. Okay? So what do we notice about these two values, specifically in a series circuit? That they're equal. In a series circuit, the current is the same, no matter where you measure it. If you were to break this here, you were to put in an ammeter, so a meter that would measure your current, you could put it in here. You're going to measure your I total, which is 3 milliamps. You could move that meter down to here. You're going to measure 3 milliamps. If you were to replace this resistor with a meter that had the resistance of 1 kilo ohm, you would measure 3 milliamps. In a series circuit, the current is going to be the same. If it's not, you've done something wrong. Okay? That's one of the hard and fast rules. In a series circuit, current has to be the same everywhere. Yes?
So what are some like reasons why you would use
If you had something else in this place that was like another resistor, you could be dropping, you would have current down there. If you put things so they were in parallel, which we'll talk about here next week or week after. Things get shorted out. Like I said, other components get into place, things like that. Like I said, if you're seeing current drops between these, you probably have something else that's going on with your circuit and you no longer have what you think it is. Okay, so now that we have that, what is our power total? Voltage times current. Yep, so power total is voltage total times current total. So we have 3 volts times 3 milliamps. So remember, this is where we have to remember what these symbols mean. So we have 3 times 3 times 10 to the negative third. The other thing to remember is it's not just 3. Okay? It's 3 times 10 to the 0. So remember earlier when we were learning about powers of 10, when we multiply them together, we can separate these portions out because it's all multiplication, so we can change the order. We now have a 10 to the 0 times a 10 to the minus 3. How do we combine those together? Add them. So now we have 3 times 3 times 10 to the minus third. So we know that milli is going to stay there for our answer. Now we can multiply these whole numbers together and we get 9. So we end up with 9 milliwatts. One of the cool things that we're going to find is in a circuit, the power total is going to be equal to all the powers in a series circuit. Okay? Everything's going to add up together. So if we had 14 resistors in here, we would find the power for each one of those resistors. We would add them up. Those are going to equal this value if we took our total voltage and our total current. Because again, we cannot create or destroy energy. We have to account for everything. Okay, so in this case, what's the power drop or power across R1? 9 milliwatts. And what's our formula? Times IR1. So again, 3 volts times 3 milliamps gives us 9 milliwatts. This is a lot of redundant stuff. The questions in Moodle aren't going to be this intensive. But I wanted to kind of show you guys a point with this, is when we do these calculations, start recognizing the current in a series circuit is going to be the same everywhere. Power is going to be the total summation of all the power drops in the circuit. So in this case, we only have one component. It's going to be the same as that value because there's nothing else to add to or to take away from it. Does that make sense? Okay, let's go through another example. So we are given this circuit. We have R1 is 5.6 kiloohms, so 5,600 ohms. And we're given a current total of 1.964 milliamps. We need to know how much is our voltage. Jeff, what formula do we use?
Is that 1.964?
Yes, 1.964. I times R. We're looking for voltage. Whatever's left in their configuration gives us how we do the formula. So voltage is equal to current total times resistance total. And in this case, we have one component, so that is our resistance total. So voltage total is equal to 1.964 milli multiplied by 5.6 kiloohms. And then we got to double check. We have amps times ohms. So that follows with what we have here. Amps, ohms, volts, watts, amps, and volts. So the red is the unit that they're being measured in. Keep that in mind. This is 1.964 times 10 to the negative third times 5.6 times 10 to the third. Okay? What's going to happen with our prefixes? They're going to cancel each other out because we can pull these guys out. So 10 to the minus third times 10 to the third is going to equal 10 to the 0, which equals 1. So when we plug this into our calculator, we can know right off the bat, those are going to cancel out and we're going to be left with nothing. Okay? Then what do we have left? And Reed, what does that come out to be? Essentially 11 volts. So one thing to remember too is this didn't quite come out to be 11 because right here we probably should have carried it out one extra digit maybe. Okay? But for all intents and purposes, the difference between 10.998 and 11 is 0.002 volts, which is percentage-wise 18 millipercent. Little bitty. So 0.00018%. Okay? That's well within our 5% as far as accuracy goes. Things are going to change when we're setting this up. This resistance value might end up being, when we get it, is like 5.63K or 5.55K or something like that. So when we do these, we will have a little bit of tolerance and a little bit of error based on these problems. So don't be worried too much when we're calculating these guys. If you drop off, so if somebody tells, if somebody was to say 10.998 volts, somebody else says 11.1 volts or 11.01 volts or something like that, they are equivalently the same thing, okay? So we don't need to get hung up on those values. If we get values that are significantly different, then yeah, let's stop and talk. Because I do have a lot of the answers for the problems I'm working through. Some of them I create on the spot, and so I am doing them with you guys. And I want to hear where, how did you get that answer? Okay? Because then it could be just simple calculation error. It could be, an understanding thing. I use it to understand and help teach you guys where where the errors occurred and how do we make sure we get back onto track to not make those. So if you do get a different answer, don't hesitate to ask, and we will work through it. That's one way, I learn is by seeing mistakes, not just my own, but other people that they make. Where did they go wrong? Because odds are I'm going to go wrong there at some point too. So kind of keep that in mind. Does this make sense? What we're doing? Ohm's law at its heart and soul is very, very basic. Okay? It can get quite complicated when we start adding more things to it, but at the end of the day, this is the heart and soul of what we're looking for. Okay, let's do another one. So one of the things too that we're assuming that when we go to measure these guys, so we're going to have our resistor here, we're going to have our voltmeter right here. We have two leads on our voltmeter. We're going to have our red and black. And then just for kicks and giggles, we're going to look at if we switch these. Okay? And I'll show you what's going to happen. So on this one, we are given 2.515 milliamps. And we're given 33 ohms. What is our voltage total? And also, what is our voltage drop across R1? So I'll give you guys a second to work through that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Okay, everybody ready? So one of the things I like to do, may make me a little bit sadistic, but I enjoy it anyway. Spencer. Now, one of the things I like to do is I'll usually add people's names on there about 4 or 5 times, so there's a lot of them. And then when it comes to you, I'll have it so it deletes your name off of it. So you're not always going to be called on. And then sometimes I even have it too is when it comes through and you're not in the room, like if you stepped out for a bathroom break or whatever, and your name gets called on or you happen to be absent, I throw another one in. So, just because it's fun. So, Spencer, what formula are we going to use to start with? Okay? That is correct. Ten to the 0. Because anything raised to the 0 power is 1. 0.08145. 415. Okay, and volts. Okay. Okay. Okay, anybody agree with that, disagree with that? Good? Okay. What number did you get? Okay, so we're all within the same ballpark. So in this instance, like I said, this is a correct number. One thing I would probably do, just because there's a lot of digits on there, is I would convert it to millivolts in this case. So I would move this in. So this is times 10 to the 0. I would want it to go to times 10 to the negative 3. So we're making that number smaller, the exponent smaller. So which way do we move the decimal point? To the right. Making this side bigger by making this side smaller. So we end up with 84.15 millivolts. Like I said, both of those are correct. I just prefer to look and see my numbers in terms of, these easier to write, quicker values. A lot of times when you're going to be working, you get these extra zeros in there, it's going to jam you up. At least it does for me. So that's why I like to put things in those ones. Also, depending on what the question wants your answer in as well. So, okay. I think we got time for one more question. The what? Oh, yes. That was the other part. Yes. So, forgot about that. Thank you for bringing it up. This will be our last question. So, when we have our meter connected up like this with the leads in the orange writing, we have red connected here, black connected here. So red is our positive side, black is going to be our common or our negative side. So remember when I said we have basically a virtual ground, this is our reference point. When we hook our meter up, we put a red spot here, the black probe here, we're going to measure 84.15 millivolts. Because remember, the polarity is like this. because it's connected to the positive side. When we flip our meter and connect it up backwards, so basically now this is reading positive, this is reading negative. It's assuming this side's going to be larger than this side as far as the potential energy, the voltage that it has. When it's looking at this guy, it's now backwards. So when we have the green probe, our voltage drop across R1 is going to be negative. So when we get into lab, you have to understand what is the polarities of what are they supposed to be, and when I hook up my meter, where is it going to go? That's why this is important, otherwise to just assume that coming off the negative is our ground. Okay, our reference point. You're going to hear that phrase when we get more into AC. What is your reference point? What is it doing? That kind of stuff. Does that make sense? Because basically your meter's looking at it backwards, expecting a higher potential here than here, but it sees it backwards and it goes, wait a minute, this is backwards, so I'm going to just simply tag it with a negative sign. I'm going to internally reverse what I'm looking at. Yeah, that one would be technically wrong. Because we're going to be assuming that your probe is going to be here on the negative down there and not flip the other direction. Okay, any questions about that? All right, that's all I have for class today. Again, tomorrow we'll be going over some more of the Ohm's law. We'll start in with series circuits, a little bit more in depth. We'll start splitting these up a little bit more, having more components, which actually gets us a little bit ahead for next week. But honestly, I'd rather be a little bit ahead than dragging behind too much. So, unless anybody has any questions about the quiz, we'll take those first, and then after that, we'll move into more of the series circuit understanding. So, okay. Remember, work on your papers. If you have questions, please let me know. Your research stuff, it is due Friday. So we still have 2 more days before those reports will need to be due. They're not anything special. Remember, just a 1-2 pager in your presentation. Yes. You can either bring them in or you can submit them online.